Hello, good evening, Donald. Hello, Donald, good evening. Hello, Donald.
Yeah, good evening, sir. I can hear you.
Okay, can you hear me?
Yes, sir, loud and clear. I can hear you and I can see your screen.
Okay, all right. So we are going to start immediately. First of all, I want to say happy Easter to you all. And welcome to week 7 facilitation for CHM102. Today, we are going to be discussing the reactions of alkene. Remember last week, we discussed alkenes generally and also went further to look at their synthesis or preparation as the case may be. So today we are going to be looking at the reactions of alkenes. So in every alkene, there is one pi bond. In every alkene, there is one pi bond, and in every bond, there are 2 electrons. So pi bonds generally are weaker than a sigma bond, and therefore, it is expected that the breakage of a pi bond will be faster and it will happen at more favorable condition than that of sigma bond. Recall that when we discussed the reactions of alkanes, we made mention of the difficulty in breaking sigma bond, for which alkanes usually undergo free radical reactions. However, in alkenes and alkynes, these free radicals are not part of the major reaction mechanism. And this is simply so because of the presence of a pi bond. So the majorly, alkenes undergo addition reaction. In addition reaction, the new incoming molecule is added to the alkene without any other thing being given up. Like what you have here, you see this is our alkene, and then reacting with YZ. YZ could be any other thing, and you can see that it has been added here without generating any other product. So because the energy required in breakage of alkane or sigma bond is higher than that of energy required to break a pi bond, addition reaction of alkenes are usually exothermic. You know, when a reaction is exothermic, they evolve energy, unlike endothermic reaction that needs supply of energy before they can take place. So they are exothermic because the energy required to break a sigma bond is higher than that required to break a pi bond. The pi electrons are loosely held by the nuclei and are thus easily available to electron-seeking reagents. An electron-seeking reagent is a reagent that is deficient in electron, and such reagents are usually called electrophiles, so or electrophilic reagent. While an electron-rich reagent are reagents that are rich in electron, okay, and they are usually called nucleophile. They are nucleus seeking, just like electrophile is electron seeking. All right. So we are looking at electrophilic reactions of alkenes. Just using this one slide, we are summarizing them. Then we will now start going one by one to look at each of this is a halogen reactions of alkene. Number one is halogenation, which is also called hydrohalogenation. So you can say hydrogen here, you can see halogen here being added, also called hydration. Hydration. Sorry, I had an interruption. So as I was saying, in hydration, you have addition of water. Okay. Then this can be done either using water and acid, like sulfuric acid, or water in mercuric acetate. This second one is usually called mercuration, oxymercuration, demercuration. We are still going to see it. Then from addition of water or hydration, we have hydroboration. In hydroboration, we add hydrogen and borane. And then from borane, you can get OH. Then we have a very important reaction called ozonolysis. In ozonolysis, we add ozone, which is O3, to an alkene. Then from ozonolysis, we have hydroxylation. In hydroxylation, we use either potassium permanganate, KMNO4, or osmium tetraoxide, OSO4. Any of these will add 2OH to the carbon-to-carbon double bond. So you can see the product here. Then we have epoxidation. In epoxidation, we use what is called a per-acid or peroxide, okay, to add an oxygen atom between the two carbon. You can see it here in the product. Then we have addition to conjugated diene. Conjugated diene. So this is hydrogenation or halogenation, but instead of what we had here, where there were only one carbon-to-carbon double bond, in this other one, there are two carbon-to-carbon double bond. And that will give us either 1,2 addition product or 1,4 addition product. We are still going to look at all of them in details. Then the last but not the least is Dice-Adder reaction. Dice-Adder reaction. In Dice-Adder reaction, you have diene and then dienophile coming together to give you a cyclohexene. So invariably, we have considered 1, 2, 3, 4, 5, 6, 7, 8, 9 different types of reaction which alkenes can undergo. So let us quickly take a look at them one by one. So the first one is halogenation. In halogenation, we are talking of addition of halogen, okay, to an alkene. Let me also say that this reaction is not only for alkene. Even alkynes, which is carbon-to-carbon triple bond, undergo halogenation reaction. As a matter of fact, once there is carbon-to-carbon unsaturation, then there is possibility of halogenation. So in halogenation, you use a halogen. You can see here, we are using bromine, BR. Then this is the nucleophile, while this is the electrophile. So reaction originates from nucleophile to an electrophile. So you see it picks this proton, this bromine or bromonium to give this, okay? So the bromine is going to now form a epoxide-like structure, which is equivalent to this. And then there will be permanent breakage of this bond, and then permanent formation. This is one electron. So half of the electron comes here, half of the electron comes here. And then you have this molecule, okay? And then you have this. So you can see in halogenation of alkene, you get dihalo products. Remember, we started with this, and then look at the products here, which is dihalo, dibromoethane. So this is the dibromo group. Now, the question is, why is the bromine group placed in the opposite direction? It's very simple, because of steric hindrance. You know, steric hindrance will likely favor the opposite direction. That is not to say that if you write the bromine on the same side, that you have committed a serious error. Hydrohalogenation. In hydrohalogenation, you are introducing hydrogen and a halogen. Example of compound or reagent that can be used for hydrohalogenation is HCl, halogen acid. Okay, so you can see what you have here. Okay, you can see the products. However, in hydrohalogenation, in hydration, and so many other reactions, when we are working with symmetrical, when we work with symmetrical alkenes, when an alkene is symmetrical, it simply means that when you bisect at this point, what you have at this end and what you have at this end are going to be the same. So when you have symmetrical alkene, you don't have problem with hydrohalogenation. However, as soon as you have unsymmetrical alkene, then there is going to be a law that governs the product that will be formed. A typical example of an unsymmetrical alkene is this. You can see at this carbon, we have only 2 hydrogen. At this carbon, we have 1 hydrogen and a methyl group. So the 2 attachments to the carbon double bond are not equal. And that is called unsymmetrical. And in this kind of unsymmetrical alkenes, there is going to be 2 different products. One is when the hydrogen come to this place, as you can see here. You see the hydrogen came to here to give you CH3, and then the bromine came to this place to give you CHBr. The next product is when the hydrogen comes to this place, okay, to give you CH2, and then the bromine comes to the terminal to give you Br. These are the 2 major products. Which one is going to be in more proportion? We shall find out that in the next slide. There is a rule called Markovnikov's rule. Markovnikov's rule. Markovnikov's rule. And this rule is saying that when you have an unsymmetrical alkene and there is hydrohalogenation, the hydrogen tends to go to a position where there is more hydrogen. That is the simplest definition way to define it. You can see in this molecule, here you have 2 hydrogen on the carbon, 1, 2. In this carbon now, you have only 1 hydrogen. So Markovnikov's rule is saying that this hydrogen from HBr prefer to come to this place, while the Br will come to this point. So you see why. The first thing that happens is the generation of a carbocation. Okay, so the double bond here, the pi bond, picks this hydrogen. Okay, you can see the hydrogen here. It picks the hydrogen. And then after picking the hydrogen, you can have either this or this. That is to say, if this carbon was the one that picked the hydrogen, you are going to have this. You can see the yellow hydrogen is on that carbon. However, if this carbon was the one that picked the hydrogen, you are going to have this. You can see the yellow hydrogen is at this position. Now, for a carbocation to be stable, there is a rule governing that. A tertiary carbocation, we already mentioned this early enough, that tertiary carbocations are more stable than secondary carbocation, and then secondary carbocations are more stable than primary carbocation. So you can see this is a secondary carbocation, and this is a primary carbocation. So this is going to be more. This is more stable, so it's going to be more. And therefore, you are going to have more of these products formed, okay? You are going to have more of these products. You can see the products here than this. And that is simply what is called Markovnikov's rule. By rule of thumb, the easiest way to remember Markovnikov is when you have this kind of molecule, the hydrogen should go to where there is more hydrogen. You can see you have two hydrogen here, while the bromine will go, or the halogen will go to where there is lesser hydrogen. This is still Markovnikov's rule. We are giving more example. You can see here, this is exactly what we did earlier, but in that one we used hydrogen bromide. Here we are using hydrogen chloride. So you can see CH2 here, you can see CH. So the hydrogen, the blue hydrogen, following Markovnikov's rule, will go to this position. So while the chloride goes to this position where there is lesser hydrogen, and that will give you these products. Okay, not this. This one is not the main product. Then the second example is here. You can see even though this is a ethene, it is not symmetrical. It is not symmetrical because here you have CH2 and here you have only CH. So you have more hydrogen here than here. So hydrogen, this hydrogen, blue hydrogen will come to this place, while the bromine will come to this place. That is Markovnikov's rule. Then let us look at a factor that it affects the Markovnikov's rule. This factor is either called peroxide effect or Karash-Mayo effect, or anti-Markovnikov's rule. The three of them are saying the same thing: peroxide effect, Karash-Mayo's effect, anti-Markovnikov's rule. You are saying the same thing. And anti-Markovnikov's rule is saying that in the presence of a peroxide, the hydrogen, instead of going to points where there is more hydrogen, instead of coming here, it will move to where there is lesser hydrogen. While the bromide will now come to where there is more hydrogen. That is anti-Markovnikov's rule. So you can see what we did here. This is no peroxide. In the absence of peroxide, you expect Markovnikov's rule to be obeyed. And so the Br will come to where there is lesser hydrogen, and then the hydrogen will come to where there is more hydrogen. However, in the presence of a peroxide, this is a peroxide. In the presence of a peroxide, is opposite of what happened here. So this Br now will move to this position, and then one hydrogen here will come to this position. And that is what we have here. So in the presence of peroxide, this is the product you are going to have. In the absence of peroxide, this is the product you are going to have. Addition of water or hydration. In addition of water, what is added? Remember, water is made of hydrogen plus and then OH. So hydration or addition of water we still follow Markovnikov's rule. So following Markovnikov's hydrogen, why the OH, we go to where there is low hydrogen or less hydrogen. So you can see what happened here to give H and OH. This OH is from water. The hydrogen is also from water. A typical reaction here is the reaction of propene with water in the presence of H2SO4 as a catalyst. This sulfuric acid here is as a catalyst. And that is why, if you remember, in the general formula we discussed earlier, you can see there is H plus there. What is standing for that H plus is this H2SO4. So first, you are going to definitely, the hydrogen is coming to this point because you have more hydrogen here, while the OH will come to this point because you have less hydrogen here. So you have 2-propanol. And then let us look at this one. One but in, or but one in, you can see hydration. The hydrogen comes to this position, while the OH comes to this position. Now, that is the product. If you come to this particular one, which is but 2 in or 2 but in, this molecule is symmetrical. This molecule is symmetrical. Remember, if you bisect it here, you have CH here, you have CH here, you have CH3 here, you have CH3 here. And remember what I told you about symmetrical compounds, that Markovnikov is useless because the product will definitely be the same. Hydration of alkene, remember we said they are in 2 processes. Either you use water and H2SO4 or use water in mercuric acetate. When you are using mercury, it is called oxymercuration, demercuration. Oxymercuration, demercuration. So this is our alkene water molecule. You can see this is OH, just like we have in Markovnikov. OH will come to this position, while hydrogen will come to this position in the last. So you see the first thing, that position of hydrogen is occupied by mercury, and then in the presence of sodium borohydride, which is a reducing agent, you now get your alcohol. Hydroboration. In hydroboration, we use borane. This is borane. The hydrogen of borane comes to this position, then this BH2 comes to this position. And then finally, it gives us this product, and this product can give either an alcohol or an alkane, depending on the next thing that happens to the borane. So hydroboration is a typical case of anti-Markovnikov. Remember, in Markovnikov, the hydrogen goes to where there is more hydrogen, and then the other component goes to where there is less hydrogen. However, in hydroboration, you can see the hydrogen is going to where there is less hydrogen, while the BH2 goes to where there is more hydrogen. So if after getting this product and you have hydrogen peroxide, you are going to go with propanol. With hydrogen peroxide, you get propanol. However, with acetic acid, you are going to get a propane. Ozonolysis. Ozonolysis is the reaction of ozone, O3, with alkene. Even alkynes also undergo this particular reaction. So where does the ozone attach? At the point of this carbon-to-carbon double bond. You can see what we have here, which is called ozonide. Okay, you can see this is the ozonide. Okay, so you see carbon to oxygen, carbon to oxygen, carbon to oxygen. Okay, so this is a peroxide, and then this is an epoxide. So what happens is that at the point of the carbon to carbon double bond, the ozone adds there, and there will be breakage of this bond. When this bond breaks, okay, you are going to get ketone and aldehyde. We are getting aldehyde because of this hydrogen, because of this hydrogen. If there is no hydrogen here, assuming it is R2, then we are going to get 2 ketone. Then if there is no R at all, then we are going to get 2 aldehyde. Then also, there are things that can happen to this product. If we have a strong oxidizing agent, an aldehyde is susceptible to further oxidation, and so this aldehyde will now give us carboxylic acid. So this is a typical example. You have 1, 2, 3, 4, 5, 6. So the ozonoid will form between these points, and then this is the point of a breakage, so that you form a molecule where you have 1, 2, 3, 4. And the carbon to oxygen double bond is going to be at this position. The next carbon to oxygen double bond is going to be at this position. And because of the 2 hydrogen you have here, because of this hydrogen and this hydrogen, it simply shows that the product of the ozonolysis of this molecule will be aldehyde. You can see it here. However, if the double bond moves from this position 2 to position 3, you can see the double bond here. We are still going to have 2 aldehyde. However, if instead of 2 hydrogen as it were here and here, we now have hydrogen and CH3. If we now have hydrogen and CH3, we are definitely going to have an aldehyde from here because of this hydrogen, a ketone from here because of this carbon. Hydroxylation. In hydroxylation, like I mentioned earlier, we prepare a diol. A diol is a molecule where you have 2 alcoholic or 2 OH group. So in this particular molecule, you can see potassium permanganate, KMnO4, or tetraoxomanganate 7. Potassium tetraoxomanganate 7, and then osmium tetraoxide. Any of these will give you a diol from an alkene. Epoxidation. In epoxidation, an epoxide is formed by the reaction of alkene with what is called per-acid. A per-acid is an acid, a carboxylic acid that contains extra oxygen. Remember, normal carboxylic acid is CO2H, but in per-acid, you have CO3H. So a per-acid is 1 oxygen more than a normal carboxylic acid. So you look at what you have here. This is an alkene reacting with per-benzoic acid. Remember, this is benzoic acid. You see COOH. Here you have COOH. So there will be donation of 1 of these oxygen to form an epoxide. Addition to conjugated diene. In a conjugation diene, the bromine which you are introducing could add to 1,2 position, or it can add to 1,4 position. All of these positions are very feasible because of the presence of 2 double bonds. So if it adds to 1, as soon as the first bromine is attached, we have this carbocation. This carbocation and this carbocation are in resonance structures. Okay, you can see this and this. This and this are the same thing almost. So what happens is that when the second bromine attacks, if you are using this, the second bromine will come to this point, and that will give you 1, 2. If you are using this, the second bromine will come here, and that gives you 1, 4. Dice-adder reaction, or what is also called 4+2 cycle addition reaction. This is also called pericyclic reaction. What happens in dice adder was simply a reaction of a diene, a conjugated diene. The diene must be conjugated. A conjugated diene, a diene contains at least 2 carbon-to-carbon double bond. We have discussed this. A conjugated diene and a dienophile. A dienophile is a diene lover. So a dienophile wants diene, and diene has the capacity of reacting with dienophile. One simple thing one should recognize about this reaction is that it leads to the formation of a ring. A cyclic molecule is always formed. So you see here we have 1,3-butadiene and ethene to give cyclohexene. So look at the simple mechanism. And this mechanism is why the diene must be conjugated. If the diene is not conjugated, then pericyclic reaction will not take place. So you see first, okay, the electron-rich diene attack this position, and then this bond delocalizes to a position between 2 and 3. And because these are conjugated, as soon as this delocalizes, it prompts the delocalization of 3 to 4 carbon-to-carbon double bond to form a ring system, which is this. You can see one of these double bond was used to form a bond between this and this, while one of these double bonds was used to form a bond between this and this. And then this remaining double bond will resmise to 2,3 position. So you can see where we noted new bond. This is a new bond that was formed. This is also a new bond that was formed. Other examples of dice adder reaction. Other examples of dice adder reaction. We have this. This is our diene. This is a dienophile to give this molecule. We have another example here. This is a diene. This is a dienophile to give this molecule. The simple question one will ask here is, this is not an alkene, but this is alkene actually. And then this is an alkyne because it contains triple bond. So that is why instead of 1 double bond here, we are going to have 2 double bonds. And then this is also the reaction. Please. There is a carbon-to-carbon double bond here. There is a double bond between this carbon. There is a double bond here. So, and that will give us this molecule. Okay, so what we have done so far is to look at reactions of alkene, starting with halogenation. We also looked at hydrohalogenation. We looked at hydration, either with water and sulfuric acid or via oxymercuration, demmercuration. We also now looked at ozonolysis. We looked at hydroboration. We looked at conjugated diene, and then we also looked at dice adders reaction. All of these are some of the reactions of alkene. There is one which we may be leaving behind, but it's very notorious to be forgotten, which is hydrogenation. In hydrogenation, just like you have in alkylation, in hydrogenation, what happens is the reaction between hydrogen, okay, and alkene. That is what happens in hydrogenation. Hydrogen and alkene to give a saturated molecule. So let's take your questions. Let's take your questions. John. Hey, John, are you there? John, are you there?
I'm here, sir.
Okay. Do you have any question?
No, sir.
No question.
No,
Everything is fine?
Yeah.
Okay. That's fantastic. Donald, do you have any question? Donald. Okay, Miriam.
Yes, sir.
Miriam, your question, please.
I don't have any question.
Huh?
I don't have question.
You don't have question?
Yes, sir.
Okay. Donald is telling us that he doesn't have any question, that we can move on. He doesn't have any question. Okay. In inform Eibio.
Yes, sir. Good evening, sir.
Any question?
No question, sir.
Okay. Nwafọ. Mary Louisa. Nwafọ.
Sir, I don't have any question.
No question. Okay. Nwigwe Grace. Nwigwe. Any question, Nwigwe?
There's no question, sir. Good evening, sir.
Okay, no question.
Yes, sir.
Shuaibu Salihu. Shuaibu. Shuaibu Salihu. Shuaibu, are you there? Okay. Since everybody said there is no question except Shuaibu, whom we are yet to hear from, I want you to quickly, in a sheet of paper there, show me how this product was formed. Using arrow, show how this first product was formed. Turn on your video, let me see what you are doing. Using this arrow, show me how this product was formed. Are we together?
Sir, which product?
Huh?
Which product?
Product one. Look
Okay.
at it here. This product, using arrow, show how this product is formed. Use arrow to show how the product is formed. Shuaibu Salihu, you were raising up your hand. Does it mean I have answered the question you wanted to ask? I asked you to turn on your video so I can see what you are doing.
Hello, sir.
Yes.
Hello, can you hear me now, sir?
Yes, I can hear you loud and clear.
I said this is the first time I attended the class, so I may not be able to meet up with what you want to ask for the class for moment now. That's why I raised my hand.
This is your first time of joining us?
Yes, sir.
Where have you been?
Truly, I was very so happy. Sometimes I was forgetting about the time. Sometimes I did forget about the time schedule. So that is the, as I just log into my WhatsApp, so someone just forward the link to me. Now that's why I joined the class at the moment.
Is it possible you have not been getting the mail we sent? You don't get our mail?
The first time I joined it, sir.
Okay, no wahala. So
Yeah.
please, let me share my email address so that one can still send mail.
Okay, sir.
Can you see it? My email address is right there as a message. Check the message. At the end of the class, if you have not been getting mail, please just send me, hi, I am so person, a student of CHM102. Just send it, then I will include you. Possibly the email address you have at the course page is not going because actually I'm supposed to have over 800 students from what I have on the course page. Surprised most of you guys are not. Okay, so who has finished the classwork? Who has finished? Nobody. Miriam,
Yes, sir.
are you done with the class work?
No, sir.
Yeah?
No, sir. I'm almost done.
Okay. John, are you done with the classwork?
No, not yet, sir.
John?
Not yet, sir.
But you are working on it.
Yes, sir.
Donald, what about you? In inform, Ebio, are you
Yes,
done
sir.
with the classwork?
No, sir.
Ebio,
Yes, sir. Yes, sir.
are you done with the class exercise?
No, sir.
This thing is not something that can take 10 seconds. It's too straightforward to waste somebody's time.
Okay. Sir,
Has anybody finished? Huh?
sir.
Has anybody finished? I said using arrow, show how this product was formed. Has anybody finished? Who has finished? Nobody.
Sir?
Who has finished?
Sir, I finished.
You are finished. Let me see what you have done.
Dr. So this one.
Yeah?
You can see. Uh-oh.
Who said she has finished? Is it Miriam?
Yes.
Huh?
Yes.
Okay, let me
So
see what you have done.
this one.
Oh yeah, hello. Eh? Papa,
Yeah.
Okay. 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 Who else has finished? Okay. So I will quickly. I will quickly refer you to something which we have done earlier. I'll quickly refer you to something which we have done earlier. And that is this. Please come back here. Can you see the arrow we have here? Can you see it? Hello, can you see the arrow here?
Yes, sir.
Aha, that is the mechanism. So the difference between what you have here and this one is just the presence of this aldehyde group. However, this aldehyde group is not part of the mechanism. So the mechanism is that this double bond will move to this position, and then this double bond here will come to this position, and then this one now will come to this position to form a new bond here, and then this one form another new bond this other place. Please, I want you to go through everything we have done. If you know you have not been getting our mail, I've just sent across my email address. Send me your email address and request. Introduce yourself, and I will send you the PowerPoints from week 1 to week 7. By next week, we will be concluding facilitation for CHM102. And I really want you people to engage me based on what you have read on your own, and also based on what we have taught during the live session. Please, it is very important you do that. Otherwise, you are shortchanging yourself. Do visit the course page to use the link and download the video for the live session so that you will not be left behind. Till next week, enjoy your day. All right, so see you next week.
Okay, thank you, sir.
Thank you, sir.
All right. Make sure everybody must have question next week. It's a must.
Okay, sir.
Everybody must have question next week.
All right, sir. Thank you, sir.
All right.
Yeah.
Wọ́n wò pé tí mọ̀ ẹgbẹ́ tí lọ́dún jáde jẹ́ nǹkan yìí náà. Wàláì, máìndì mi dẹ̀ sọ bẹ́ẹ̀. Mo gbàṣẹ ìwà kódà mo gbàṣẹ tí wọ́n ní jẹ̀dẹ̀ ní agbọn sọ́dọ̀ àkọ́ drop pẹ̀ àwa wá lọ tó gbọ́dọ̀ là máa gbé òkúta yìí. no,